All right, example 7, find the limit of the following sequence. So thankfully, all of our understanding of limits from Calc 1 carries over to sequences. So the above theorem says that if you have a function that's continuous, then even if you plug in your sequence terms into a function and then take the limit, it's the same thing as if you take the limit first of the sequence and then just apply that function to the limit of the sequence. So that's exactly what we have here. We can think of this 3n over n plus 1, we can think of it as its own independent sequence, call it b sub n. Then we have a function, let's say f of x, which is e to the x. So a sub n is really f of b sub n. So the limit as n goes to infinity of a sub n is the same thing as the limit of whatever a sub n is equal to. A sub n, we just argued, is the function f applied to the general sequence term b sub n. So then this theorem allows us, since f is continuous, we can pass the limit through the function and just take the limit of b sub n. So the limit of b sub n is the limit of this expression, and by the technique of dominating terms, we have 3 to the n as the dominating term in the numerator and n as the dominating term in the denominator. So what's the ratio of the coefficients? Coefficient in the bottom is 1, so 3 divided by 1. So the limit of b sub n is 3 divided by 1, or just 3. Well, our function is e to the x, so this is e to the 3, and that is the limit of our sequence. All right, example 8, we're going to talk about bounded sequences. So this is a sequence that is sort of trapped either there's a ceiling on the sequence, so the sequence can't go above this sort of arbitrary ceiling or this high point, or bounded from below, meaning there's some sort of minimum or some sort of floor. So let's think about an example of a sequence that is bounded from above. Bounded from above. So an example for this sequence could be the sequence 1 over n. It's bounded above by the number 1. So what's important here for either bounded above or bounded below, what's important to remember here is that these inequalities are inclusive. So it's not saying the sequence never is equal to this upper bound. It's just that it never goes above that upper bound. So it can actually touch the ceiling. It just can't go through the ceiling. So this is bounded above by 1 because as n gets larger, the sequence terms get smaller. So the largest the sequence term would have to be the very first term of the sequence, which corresponds to n equals 1, which is 1. So that's why it's bounded above by 1. So bounded from below. So something that just it increases, but it's bounded below. Well, I guess it doesn't even have to increase, really. Could decrease. For instance, 1 over n is also bounded below by the number 0. These numbers get arbitrarily close to 0, but they never actually get smaller than 0, and they never dip into the negatives. In fact, they never touch 0 either. So the same sequence is bounded above by 1, it's bounded below by 0. It does actually achieve this value of 1, but it never achieves this value of 0. So a sequence is bounded if it is both bounded above and below. So a sequence that is bounded would be, well, this 1 over n, because we just demonstrated an upper bound and a lower bound. So that is bounded. So I can say something like, this implies that 1 over n is for all n. Now, give an example of an unbounded sequence. Well, just the sequence n. As n goes to infinity, as we look very far down the sequence, look at the later terms of the sequence. So as n goes to infinity, well, we have n that's we have n goes to infinity. Seems silly to say that, but that works out. As n goes to infinity, our sequence, being defined to be just n, must also go to infinity, and therefore it diverges. Okay?